Welcome to Pencil College. And guess what? We are at chapter 2.9, the very last chapter for this topic on logarithms. Okay, so in this chapter, we will learn how to apply all that we have learned in the previous sub-chapters to solve simple practical problems. And I would personally think this is what is most applicable in real life. Okay, so let's look at example number 1. At the beginning of 1990, the population of a town was estimated at 12,000. The population increased so that after a period of n years, the population is given by this function that you see over here on the screen. Estimate the population at the beginning of 2005. Okay, so at this point in time, let me just clarify some things. So in the year 1990, okay, your n will be equivalent to 0, okay, because n is the number of years after 1990. Okay, so for example, in 1991, your n will be 1. Okay, so in 1992, your n will be 2, so on and so forth. Okay, so my question would be, in 2005, what is n? Okay, so if you take 2005 minus 1990, you will just get 15. So in 2005, n should be 15. So the population required, okay, is given by this function. So it's just 12,000 multiplied by e to the power of 0.07 times n, and n is 15. Okay, so if you round this off, you will just get 300, okay, to 3 significant figures. Okay, part B. The year in which the population would be expected to have first increased to 90,000. So now we want the population function, okay, the population, this is my population, to be equals to 90,000. Okay, wrong. I think I should be using an inequality sign. Okay, why do you think I will be using an inequality sign? The reason is because I want the population to exceed or first increase to 90,000. Okay, so I will first divide my 12,000 over. Okay, so this will be greater than 90,000 divided by 12,000. Okay, and in order to evaluate this, I'll take ln on both sides of the equation. So i.e. to say 0.07n is greater than the ln of 90,000 divided by 12,000, which is just 7.5. Okay, and finally, to solve for n is greater than ln 7.5 divided by 0.07. So n should be greater than 28.8. Okay, so if n is greater than 28.8, then the nearest possible value for n should be 29. Okay, why do I round it to 29, not 28? Because if it takes 28.8 years, okay, for the population to exceed 90,000, then 28 years will not be sufficient. It's either I go more than 29, okay, like for more than 28.8, like for example 28.9 or 29, for example. Okay, so I will pick the number 29. Okay, the next tricky part is to state the year. Okay, so going back to what we did previously, if n is 0 in 1990, then in 1991 n will be 1. So my question will be, if this continues, in what year will n be 29? Okay, so if you count, it should be the year 2018. Okay, therefore the answer for part B is year 2018. Okay, move on. In example number 2, the mass of any radioactive substance present at time t days after the first being observed is given by this formula that you see here. Find the value of m where t is 20. Okay, so the first part is rather easy. So we will just sub t equals to 20 into the given equation. So m is equals to 32 e to the power of negative 0.02 times 20. Okay, so you just press this in your calculator and you should get this over here. okay, which is roughly 21.5. Okay, and take note that the mass is given in grams, so it's 21.5 grams. Okay, in part B, we want to find the value of t when the mass is half of its value at time 0. Okay, so first and foremost, let's find the mass at time 0. So to find the mass at time 0, we'll just sub t equals to 0. So m is equals to 32 times e to the power of negative 0.02 times 0. Okay, and this is just equals to 32. Okay, because this term here goes to 1. Okay, anything to the power of 0 is just 1. Okay, so if the mass is 32 at time 0, then what is half of this mass? Okay, then half of this mass will just be 32 times half, which is 16. And we want the value of t when the mass is 16. So now we will sub m equals to 16, okay, into the original equation. So 16 equals to 32 e to the power of negative 0.02 t. And how do we solve this? We divide the 32 over first. So 16 over 32 equals to e to the power of 0.02 t. And then this is just half. Okay, so to get rid of the exponential, we'll take ln on both sides of the equation. So this will give me 0.02 t. So finally, t is equals to ln half divided by negative 0.02. And if you just round this off, you should get 34.7. Okay, and this should be in days. Okay, move on to example 3. In this example, we have a cup of hot coffee left to cool on the table, so that t minutes later its temperature is t degrees Celsius, given by this function that you see over here. Find the initial temperature. So for part A, take note that initial temperature simply means, or simply implies, that we want to find the temperature when time is 0. So when time is 0, t will be 27 plus 58 times 0.92 to the power of 0. And this term, okay, anything to the power of 0 is just 1. Okay, so this will be 27 plus 58, which is just 85 degrees Celsius. Okay, that should be manageable. Now for part B, we want to find the temperature 5 minutes later. So at time 0, this is the temperature which we found in part A. So 5 minutes later, now we will substitute t equals to 5. Okay, so 5 minutes later implies that we need to substitute t equals to 5. Okay, so small t equals to 5. So big T, which is your temperature, is just this to the power of 5. And if you just round this off, okay, you'll get 65.2 degrees Celsius to 3SF. Okay, in part C, we want to find a time when the temperature is 50 degrees. So now my big T, so when the temperature is 50 degrees. So this means that my big T is equivalent to 50. So if big T is 50, okay, substituting this into the given function over here, I'll get 50 equals to 27 plus 58 times 0.92 to the power of t. Okay, so to solve this, shift the 27 over to the left. So 50 minus 27 equals to 58. 0.92 power t. This is just 23. Okay, so I'm going to do something concurrently. I'm going to divide the 58 on the right side of the equation over to the left. So this will give me this. Okay, and to get rid of the 0.92, or to solve for t rather, I will take ln on both sides of the equation. So ln of 23 over 58 equals to ln of 0.92 to the power of t. Okay, so take note that this t, the power t, can be brought down to the equation over here. So let me continue over here. So ln of 23, okay, over 58 is equals to t times ln 0.92. And finally, to solve for t is just ln of 23/58 divided by ln of 0.92. And if I round this off, I'll get 11.1 minutes. Okay, hope you enjoyed this few examples. So in summary, in this chapter we learned how to apply indices and logarithms to solve simple practical problems. And just want to highlight that in practice, many growth or decay activities can be modeled by the exponential function. Okay, so at this point in time, let me leave you with a practice question. Thank you for watching this video and joining me throughout for this entire chapter of indices, surds, and logarithms. For more videos, please log on to pencilcollege.com.